Okay, so today we are talking about axiomatizable or definable classes of models. So this is the 12th lecture in advanced course in classical logic. In one of the previous lectures, we had the Chrysler's theorem that gave us necessary and sufficient condition for a class of models to be axiomatizable or to be finitely axiomatizable. So these are two options, axiomatizable and finitely axiomatizable. Today we will see that there are two more natural options, and they form a very natural hierarchy. These four options will be called species of elementary classes. The word elementary usually in literature is the same as axiomatizable. Sometimes the same as finitely axiomatizable. You need to take care reading the literature. Okay, so what do we have in our situation? Just from a high level, we have a language that consists of formulas. And today we will consider only closed formulas over some fixed signature. So we fix the set of predicate symbols, functional symbols, and constants, and build closed formulas. Formulas that do not have free variables. So all variables are bound by some quantifiers. Examples will be below. So this is the syntax. On the semantic side, we have interpretations of models of with signature sigma. Each model has some set, the domain, and for every symbol from pred, it has a predicate, an n-ary predicate on this set, D, for example. For every functional symbol, we have a concrete function. For every constant, we have a fixed element of this D. So we have formulas, we have models, and there is a bridge between them, the truth relation. We know the definition that F formula A is true in a model M. Everything that we consider below is applicable to any other logical systems, any logic, any class of structures or interpretations or models. We only need that there is a truth relation. What does it mean? That the formula is true in the model. So for example, we have this signature of ordered sets. So we usually have equality in our signature. And additionally, here we have a binary relational symbol less. This is an example of a closed formula. In fact, it says that between any two elements, there is a third element. The interpretations of this signature are of this form. We have a set D, a non-empty set, and a binary relation on it. And we have some classes of models like this. For example, the class of partially ordered set, the class of lattices. Lattices can be defined using the relation, not the conjunction and disjunction, but the relation. Partially ordered to linearly ordered set, well-ordered sets, and so on. Another example uses the functional symbol. So we have a binary relation of equality, and now we have a functional symbol of multiplication. It takes two arguments, so its arity is 2. We don't have constants in both examples. This is an example of a formula. There is some t such that for any z, t times z equals z. So this first part states that there is an neutral element, the unit. So T plays the role of a unit. We don't have a unit in the signature. So we must claim that it exists in an axiom. And additionally, we say that any element has an inverse. For any x, there is y, such that the product is T. And this statement is inside the quantifier for all that exists T. So we reuse this T here because we don't have an explicit constant for the unit. Similarly, we can write the axioms of groups, and similarly for rings, fields, and so on. So we can always consider that groups have only the multiplication symbol, fields have only the multiplication and addition symbol, and so on. Interpretations now are of the form a set D and a binary function, a function with two arguments. And we have, of course, examples of some natural classes like groups, semi-groups, monoids, and so on. If we take one formula A, it defines some class of models, the class of all models in which this formula is true. Similarly, we can do for a set of formulas, gamma. It defines some class of models. Defines or axiomatizes, another term. Dually, any model has its theory. If we take one model, we can consider all formulas that are true in this model. And if we have a class of models, we can consider all formulas that are true in all models from K. This notion means that A is true in every M from K. So these are dual notions. There is some duality between classes of models and sets of formulas. So they are theories. As an exercise, I leave the following equality. If we take theory of models of theory of a class of models, we obtain the same as the theory of K, and dually here. This is an exercise. In the previous lectures, we called a class of models finitely axiomatizable if we can define this class using just one formula, a single formula A. In other words, for any model M, this model is in K if and only if it satisfies our formula A. For example, groups are the class of groups, the class of fields, of linear orders, Boolean algebras. All these classes are finitely axiomatizable. Recall that Boolean algebras are defined by quite a long list of properties. These are just axioms in some first order language, in some signature. Okay. Some basic properties. If a class is finitely axiomatizable, its complement is also finitely axiomatizable, and vice versa, of course. Secondly, the family of finitely axiomatizable classes, or the species of finitely axiomatizable classes, is closed under intersection of two classes. If we have two classes then that are finitely axiomatizable, then the intersection is finitely axiomatizable. And similarly for union. And the proof is even quite simple. If the class K was defined by some formula A, then its complement is, of course, defined by the formula not A. A model satisfies not A if and only if the model does not satisfy A. This is trivial. Where A is a closed formula, a sentence. For the item 2, if K1 and K2 were defined by some formulas, say A and B, then the intersection, of course, is definable by the formula A conjunction B, A and B. And for union, of course, we need to take the disjunction of these two formulas. So this is easy. The next notion was an axiomatizable class of models. It is axiomatizable if it can be defined by some set of formulas. possibly infinite set. We don't need this phrase. I need to remove it. So for any model, it is in our class if and only if the set of formulas gamma is satisfiable. So the set gamma may be finite or infinite. If it is finite, then our class is defined by just one formula. We can take the conjunction of all formulas from gamma. If it is infinite, then in general, we cannot reduce it to just one formula. We know examples of axiomatizable classes: infinite groups, infinite fields, algebraically closed fields. These are fields such that every polynomial has a root. For every polynomial of degree n, we can write the corresponding axiom, and then we take all axioms that correspond to polynomials of degree 1, 2, 3, and so on. So this is an infinite set of axioms. Okay. We can characterize axiomatizable classes using finitely axiomatizable classes later, but we will use the following property. Axiomatizable class, the family or the species of axiomatizable classes is now closed under arbitrary intersections, finite and infinite intersection. So if we have many axiomatizable classes indexed by some I, then the intersection is again axiomatizable. And of course, this is very easy. If we have axiomatizable classes ki, each of them is axiomatized by some set of formulas gamma I, then can you tell me what is the axiomatization of the class K?
It is union of this gamma I.
The union, exactly the union. So to the intersection of classes, the correspondent operation for sets of formulas is the union. Try to think if we have the union here, shall we have the intersection here? Of course not. Try to think why this is, there is a discrepancy. So usually in set theory, in many branches of mathematics, intersection and union behave dually, symmetrically, but here it is not. It is not the case. Okay. And this, now we can establish a different characterization of axiomatizable classes. A class is axiomatizable if and only if it is representable as the intersection of finitely axiomatizable classes, of possibly infinite family of finitely axiomatizable classes. Indeed, if our class, well, from right to left, this is trivial. If K is the intersection of finitely axiomatizable classes, then it is the intersection of axiomatizable classes, so it is axiomatizable by the previous lemma. So only from left to right is interesting here. So assume that K is axiomatizable. So its axioms are the set gamma, and gamma consists of some formulas AI. Then we can easily represent this class K as the intersection of finitely axiomatizable classes, Ki. What is Ki? Can you tell me what will be the Ki class? It must be finitely axiomatizable. It must be axiomatized by some formula or some finite set of formulas.
It is a models of some subset AI, which is finite.
Yes, just one formula. Of course, we have two different notations. After the word models, we sometimes write one formula, sometimes write a set. And if a set has just one formula, we don't write curly brackets. So anyway, so we reuse this notation for sets and for formulas and remove brackets. Anyway, So if we consider 4 models of just one formula AI, then the models that belong to K must belong to every this class. Well, this is just an easy consequence of just definitions. Now, we recall the main result from one of our previous lectures, the axiomatizability criterion and finite axiomatizability criterion, the Chrysler's theorem. A class is axiomatizable if and only if it is closed under elementary equivalence. It is defined here. 2 models are elementary equivalent if for every formula, closed formula, of course, it is true in the first model if and only if it is true in the second model. So K must be closed under elementary equivalence and ultra products. We don't need what is an ultra product today. Just remember that this is some operation on models. And it is finitely axiomatizable if both the class K and its complement satisfy the previous conditions, closed under elementary equivalence and ultra products. So this theorem is summarized in this table. The first line corresponds to axiomatizable classes. The second line corresponds to finitely axiomatizable classes. And there is an evident asymmetry in this table. We have 3 occurrences of ultra product, and the 4th cell is empty. There is no symmetry. And the reason is that this is not the whole story. There are 2 more cases that complete this picture in a nice way. So again, finitely axiomatizable classes are classes defined by one formula. Axiomatizable classes are defined by a set of formulas, or equivalently by an intersection of some finitely axiomatizable classes. Now, if we have intersection, let us take the union. And let us call a class of models co-axiomatizable if it is representable as the union of some finitely axiomatizable classes. So K is the union of Ki, where every Ki is finitely axiomatizable. And of course, we can go further. What is called a class of models quasi-axiomatizable. So this is a short abbreviation. If it is representable as the union of axiomatizable classes. So axiomatizable use intersection, and now we take union of them. And of course, we could go further and consider intersections of unions of intersections, and so on and so on. The question, should we go further, or the hierarchy stops? To reflect that we use intersection, union, and union of intersections here, I also use the following mnemonic notation. The class is elementary, the letter E, is the same as finitely axiomatizable. So in our lecture, elementary will be a synonym for finitely axiomatizable. It belongs to intersection E if it is axiomatizable. Remember that this means that K is the intersection of some classes from E. Similarly, union, co-axiomatizable. And the last, union of intersections of finitely axiomatizable. It is called quasi-axiomatizable. Now, should we continue, consider intersections of unions and even further combinations? The answer is no. These 2 second steps are the same. They give the same families of classes. A class is representable as the union of intersections of finitely axiomatizable classes if and only if it is representable as the intersection of union of elementary classes, finitely axiomatizable. So we will prove this just on the next slide. But before that, let us review the whole picture So in total, we will have 4 species of classes. Very simple classes, finitely axiomatizable, axiomatizable classes of models, co-axiomatizable, and quasi-axiomatizable. Or in our notation, we will have this picture. Great. Why does this happens? So we formulate this theorem. We will also give a third equivalent condition when a class belongs to this upper room, upper species. We need some necessary and sufficient condition in terms of a class is closed under something and something. And this something will be very simple. So for any class of models, and as you can see, this is applicable to a wide range of situations, not only to the first order logic, to model logic, to some more general situation. We only need that our language has the conjunction, disjunction, and negation. So the class belongs to this intersection of union of elementary classes, if and only if it is representable as some intersection of union of axiomatizable of finitely. So it should be finitely axiomatizable. So elementary classes, union, intersection, elementary. And the last condition is K is closed under elementary equivalence. So if a model belongs to a model M is in K and models M and N are elementary equivalent, then N belongs to K. One direction is very easy. Assume that our class is the union of intersection of finitely axiomatizable of elementary classes. So they are axiomatized by some formula Aij. Assume that we also have 2 models that are elementary equivalent. They satisfy exactly the same formulas. Then we start with M in K, and we will finish with N in K. M in K, and K is represented like this. This means that for some I, there is some J, such that our model satisfies Aij. But the model M satisfies Aij if and only if the model N satisfies Aij. So we equivalently rewrite using N, and this corresponds to N in K in K. So this is easy. Similarly, of course, we prove that A1B implies 2. So now we only need to prove that 2 implies 1A. Of course, 2 implies 1B is proved similarly, so we will only prove that 2 implies 1A. So assume that our class is closed under elementary equivalence. We need to represent this class as the union of some axiomatizable classes. We know that an axiomatizable class is an intersection of finitely axiomatizable, but we don't need it here. By definition, this union intersection E means that K is the union of some axiomatizable classes. And we claim that this representation is the following. The class K is the union of some axiomatizable classes of some class. What is M in square brackets? It is the equivalence class for this equivalence relation. All models that have the same theory as our model, the same set of true formulas. Why is this enough? An exercise. This class can be obtained as follows. First, take the model M, then all formulas that are true on this model M, and then all models that have the same theory, the same true formulas. Well, this is, of course, an immediate consequence of this definition, because we take M and consider all models on which exactly the same formulas of the theory M are true. So, as a consequence of this exercise, this equivalence class is an axiomatizable class. So we only need to prove that this union is exactly K. But if you draw a picture, this is almost obvious. K is closed under elementary equivalence. What does it mean? If we take any model from our class, then the whole equivalence class of this model is inside our K. It cannot be a part of this class is inside our class K and another part is outside. It is the whole class is inside our K. And so the K simply splits, is partitioned into these equivalence classes. And this is what we prove here. So from left to right, the inclusion. If some model is in K, then we must show that M belongs to this right-hand side. Of course, it belongs because it belongs to the class squared M. This is easy because the model itself belongs to its own class. The converse inclusion. So for every model M in K, so we need to show that this union is contained in K. Take any model M in K. Why this class belongs to K? Because K is closed under elementary equivalence. If M is in K, then any model that is equivalent to M is also in K. So the whole class is in K. And therefore, the union of them is in K. Well, this is a very easy. And similarly, we can prove. But of course, when in the proof of 2 implies 1b, we need to represent K as the intersection. Intersection of what? Try to think what do we need to take. Or we can simply use, if K is representable as the union of intersections. So if K consists of some whole classes, equivalence classes, then of course the complement of K also consists of whole classes. And equivalence class cannot be split. Part of it belongs to K, part of it belongs to the complement of K. So you can apply simply this argument to the class over line K, so the complement of K. So either you can prove directly like this, or you can simply apply the previous statement to the class, to the complement of K. There are two ways to prove. Okay, so this is just to remember what do these symbols mean. More properties. Well, the first was already mentioned. Elementary, so finitely axiomatizable classes are closed under intersection and union. If you have two finitely axiomatizable classes, then the intersection and the union, the typo, are finitely axiomatizable. Axiomatizable classes, not finitely. Axiomatizable classes are closed, of course, under any intersection. We already mentioned this on the previous slides. So if we have many classes that are axiomatizable, then the intersection is axiomatizable. For co-axiomatizable classes, a similar statement holds, of course, but not for intersection, for union. Because they are unions of finitely axiomatizable classes, so they are closed under unions, any unions. And of course, our last species of classes is closed under both intersection and union. Arbitrary intersections, arbitrary union, because it is arbitrary union of something, so it is closed under unions. And at the same time, it is the intersection of something. Well, in fact, this equality can be explained very easily. If you succeeded to build some class K using intersection of unions of intersections of unions and so on of some finitely axiomatizable classes, then by distributivity you can rewrite this representation as simply like in the disjunctive normal form, DNF, like a union of intersections of some starting classes. And similarly, you can rewrite it as a conjunctive normal form, KNF, using again the distributivity. So any class that is representable like this is representable with unions of intersections, and vice versa. So simply use the distributivity of unions over intersections and the distributivity of intersections over unions. So these are just easy statements. More properties. A class is axiomatizable if and only if its complement is co-axiomatizable. And the class is quasi-axiomatizable if and only if its complement is, of course, belongs to the intersection of unions, which is the same as union intersection. So this upper species, the biggest species, is also closed under complements. Not only under arbitrary intersection as unions, but also under arbitrary under complements. Okay. So we had this theorem, and now we have two more items. We will simply write in the table. So the last line corresponds to this finitely axiomatizable, to this statement of the theorem. The second line corresponds to axiomatizable. Now, the third line is obtained from the second line by the complement. So by this statement, class is axiomatizable if and only if its complement is co-axiomatizable. So we simply rewrite this table, this line, but for the complement of K. And the first one was proved in our theorem. A class is quasi-axiomatizable if and only if it is closed under elementary equivalence. Now the table is symmetric. And recall that the Chrysler theorem can be rewritten using the notion of compactness, not ultra products, but compactness. So we obtain also this table of criteria, and they are more easy to apply in practice. Compactness is easier, or non-compactness is easier to show for a concrete class. Let us review some examples. Let us consider fields this time, not groups, but fields. So the class of fields is finitely axiomatizable. We have, as far as I remember, 8 or 9 axioms of fields. The class of finite fields is co-axiomatizable. Why is that? For example, the class of fields of cardinality 7 is, of course, finitely axiomatizable. We can write the axioms of fields and another axiom, there exists x1, x7 that are distinct, and every element y belongs to is equal to either x1 or x2 or x7. So we have a formula that says that our field, our set has exactly 7 elements. And similarly for any other number of elements, finitely number of elements. So the class of fields of one particular number of elements is also finitely axiomatizable. And the class of finite fields is simply the union of these classes. So we take all fields of cardinality 2, all fields of cardinality 3, 5, 7, and so on. So it belongs to the second layer, to the second co-axiomatizable. Does it belong to the first layer, to the finitely axiomatizable classes? No, we already considered this argument. We can simply show that the class of finite fields is not compact. Consider these formulas. There exist exactly n elements. Every finite subset of these formulas is satisfiable in some finite field. You can simply take, we must have at least n, not exactly n, of course, at least n. Otherwise, these statements are inconsistent altogether. So at least n. So a finite subset of this set of formulas is satisfiable in some finite set. Simply take sufficiently large field. But the whole set of formulas gamma is not satisfiable because it says that we have infinitely many elements. So we have shown that it belongs to this union E. It is co-axiomatizable, but not to the last line, because we have shown that this class is not compact itself. So we use this table to show that it is co-axiomatizable but not axiomatizable. The class of infinite fields is axiomatizable. Of course, we simply take all fields, the axioms of fields, and also these axioms. There exist at least 2 elements, at least 3 elements, and so on and so on. It will be an infinite axiomatization, of course, but still an axiomatization. But it is not finitely axiomatizable. We cannot do better, because in order to be finitely axiomatizable, both our class and its complement must be compact. But its complement is not compact, because this set gamma is satisfiable in the complement. So what is the complement of infinite fields? It contains all finite fields, and it also contains structures in the signature of multiplication and addition that are not fields at all, that don't satisfy some axioms of field. So why the class, the class of infinite fields, its complement is not compact. So we can simply take this set of formulas and also add the formulas, the axioms of fields. Then every finite subset of our formulas is satisfiable in the complement. So it is satisfiable in some finite field. But the whole set of formulas is not satisfiable in the complement, because it will be some infinite field. So it will belong to our class, not to the complement. And now the most interesting, some class of fields that belongs to the upper species, quasi-axiomatizable. But first, let us add another property, a class of infinite fields of one particular characteristic P. So P is a prime number, a fixed prime number. Remember that the characteristic of a field is the minimal number P, such that 1 plus 1 plus 1 p times equals 0. If we don't have such a number p, then we say that the characteristic of a field is 0. So if we consider the characteristic p not 0, non-zero, then it is an axiomatizable class, because we simply take, like here, the axiomatization of infinite fields, and also add one formula. The characteristic of our formula of our field is p. 1 plus 1 plus 1 p times equals 0, and for smaller numbers it is not equal, it doesn't equal 0. So this is an axiomatizable class. And now consider all infinite fields of positive characteristic. So this is some combination of infinite and finite. Of course, it is the union of these classes from item 2, from item 4. So it belongs to the union of intersections of elementary. So it is quasi-axiomatizable. But as an exercise, try to show that it is not axiomatizable and it is not co-axiomatizable. So in order to show this, simply we use this table, show that neither the class is compact nor its complement is compact. This will be infinite. In one case, you need bigger and bigger sets, and in the other case, you need bigger and bigger characteristic. So this is an exercise. Show that. So this is a properly quasi-axiomatizable class. It is not. It doesn't belong to the smaller, to the lower species. Final remarks. So here we had examples about fields. Fields have two operations, multiplication and addition. It may seem that we need these strong things, some very deep structure on our models in order to build these quasi-axiomatizable classes and so on and so on. But no, we can do the same using a very, very simple signature. Besides equality, take just one unary predicate symbol. So in formulas, you can write P of X. This is a very simple first-order language. And of course, you can use quantifiers, conjunction, disjunction. Then try to build classes of models that are finitely axiomatizable, axiomatizable, co-axiomatizable, and quasi-axiomatizable. And in each case, you need to show that it doesn't belong to the smaller, to the simpler class, to the simple species. So by analogy with this, okay. But what if we consider an even smaller signature? Just equality. Then firstly, try to build finitely axiomatizable class. Of course, the class of all models is finitely axiomatizable, so there's no problem. Try to build axiomatizable class, but not finitely. Try to build co-axiomatizable class, but not finitely again. But this time show that you cannot build quasi-axiomatizable class. If you build some quasi-axiomatizable class, it will be either axiomatizable or co-axiomatizable. So the upper room in this hierarchy will be empty. And another question to think, here is a typo. Consider the signature that has only one predicate symbol, P, unary predicate symbol. Can you build all four finitely axiomatizable, axiomatizable, co-axiomatizable, and quasi-axiomatizable? So all four possible classes. So without equality. So instead of equality, it should be P here. It's a typo. So these are just some questions to think. These are tasks for the students. Okay, so this is the end of the lecture, and we can discuss some questions.